All right, can everybody hear me okay?
Yep.
Awesome. So this is a BrownBag session about unit test derived fuzzing. And yeah, this turned out to be a lot more, there's a lot to talk about here. So we won't go too much into code and seeing this run with Python, Ruby, and Go like I had originally planned. But we will cover everything we need to do to get there. There's a lot to talk about. All right, so let's get started. So who am I? My name is James Johnson. I am a staff security engineer on the vulnerability research team within the secure group at GitLab. I am Doc Savage on GitLab. That's my username. So you can see work I'm doing there. And these slides are made with a tool I wrote called Look at Me. So if you wanted to follow along, this is what you would need to do that. Basically, it renders markdown slides in the terminal so that I can mix code and bash prompts. All right, so the problem that that we'll talk about in this BrownBag session is making it easier for developers to start using fuzzing. There's a lot of things you have to do to be able to use it and use it well with a project. You have to have knowledge about fuzzing methodologies, how to know if it's working well or if it's fuzzing things that aren't even related to what you're working on. A lot of times you have to reset up environments, copy and paste a lot of code, create fuzzing harnesses to do all of the work. And then once you get everything set up, you have to actually run it, and then you have to monitor for results and tweak the settings of your fuzzer and kind of dial it in so that it's very targeted and does what you're expecting. So these are all hurdles that hinder developers from easily using fuzzing within their normal workflows. And so this BrownBag talks specifically about trying to derive fuzzing harnesses directly from unit tests. I've done another BrownBag about doing this using PiTestAuto Explorer. That has a different approach, and this BrownBag session is talking more about a general, more sustainable approach that isn't so specific to Python. All right, so in standard fuzzing situations, often the fuzzer will modify a single input and the fuzzing harness will forward that input to the target binary or target program, doing whatever setup needs to be done in order for that input to actually be processed and looked at. And this is a very simple, straightforward case. It works very well for image processors, things that process raw data. Now, for deriving fuzzing harnesses or fuzzing code directly from unit tests, things won't be quite that simple. So here is an example of a very straightforward kind of classic fuzzing harness. This is taken from the Chromium source code itself. This is fuzzing their time parser library. And again, it just operates directly on raw data. By the time, so as a developer, this is all I would need to set up. And so LLVM fuzzer, that's all part of libfuzzer. So libfuzzer itself takes care of the mutations. You can override it and provide a custom mutator, but the default is all you have to provide is the harness to forward the data to the correct targeted location within your project. So as a developer, this is all I would have to do. I wouldn't have to worry about mutation or anything. Just forward the data on. And again, it is only just raw data, so an array of bytes. And a few things to note about this, and I did already mention it, the data is already mutated, and this is called once per mutation. So if you have very heavy setup processes, as a developer, you're going to have to be aware of that to set everything up in a way that won't slow down your fuzzing. So there's a lot to be aware of as you write fuzzers. Basically, the faster your fuzzers run, the more success you'll have. If you can only fuzz a few iterations per second, it's better than nothing, but if you can exponentially make it faster, it's obviously much, much better. Now, suppose we have this Go code. We have a sum function. It accepts 2 parameters and a test function that tests it. So this might be something that I would write if I'm writing a basic math library. Now, it does look very similar to the fuzzing harness here. It's a single function, and it does things inside of it. It sends data onto the target library or project in a targeted manner. And the target is this sum function here, except now we have 2 variables and it's not raw bytes. So that right there would make it harder to make it work with libfuzzer or other types of fuzzing libraries. So the rest of this BrownBag is mostly going to talk about how we can take these unit tests and translate them or map them into a similar type of setup as what fuzzing is, and map them into the same type of setup that fuzzing usually uses today. All right, so let's look at this one more time. So this is called once per iteration. There's mutation that happens. It's taken care of by libfuzzer though. We don't have to do it ourselves. There is a corpus of data. We will talk about that, but it is basically a way of seeding the fuzzer so that you have initial known good starting points to start from. Otherwise, you start with an empty data and you have to guess the correct format, or the fuzzer does. It also keeps track of whatever the fuzzer deems as interesting, and we'll get to that as well. So these are also usually feedback driven, and there's only 1 parameter fuzz at a time. Now, if we look at this though, we could easily put this in a loop, call it once per iteration. We'd still have to modify some of the parameters, so we have to take care of mutation. It's not easily supported. The corpus, you have to think about it totally differently. It is not just a collection of raw sets of bytes in the corpus. It's a lot more complicated when you're fuzzing function calls or multiple function calls from a unit test. Feedback driven. This should be very easy to map, and we'll talk about that. 1 input parameter fuzz at a time. I did want to put this in its own category to talk about because it does pose, it is a different problem set than just fuzzing a set of bytes. All right, so called once per iteration. This could have just been a bullet point, but there's actually a little more to it than that. So unit tests have setup and tear down. So if we look back at this, there is some setup here. So it creates a string and then uses the string and parse time string. Now, if you look at, say, a libpng function for libfuzzer, there's maybe 50 lines of setup code before you actually forward the data to libpng. So that concept still applies, but with unit tests, you have to be aware of the testing framework and still maintain that setup and teardown. And this was something that I ran into with PiTestAuto Explorer. I ran into database problems because I wasn't running the setup and teardown every fuzz iteration. So it would try to, in a unit test, try to create a new user and then do operations on it, but primary key constraints failed, and I was getting all of these other errors that didn't have anything to do with actual bugs in the code. So calling a test case multiple times, there's more to be aware of than just putting it in a loop. One of the other aspects though is developer logic for testing. Those can also be used during the fuzzing process. So if the developer specifically says, I care about, let's go back to this. Let's say if total, let's say the developer didn't want the sum function to ever return the value 10. Instead of checking that it's actually what it wanted, or instead of checking that 5 plus 5 equals 10, the developer actually cared about the total never being equal to 10 for some reason. We could maintain that logic from the developer during fuzzing and shake out cases where that still might be the case. All right, so mutating binary data is very straightforward. It's very simple to change a byte, add a new byte, mix things up, and you can add all types of logic on top of it. For example, this is the Go Fuzz Mutator. There's actually 19 different cases in the source code for this. This is just as many as would fit on the slide. Often it has to do with these types of things: removing bytes, treating say 4 bytes in a row as an unsigned integer, and incrementing, decrementing, shifting left or right, that type of thing. Flipping bits, yeah, and again, every fuzzing framework has their own set of mutators, and they're kind of derived from the experience of the person who wrote the fuzzer. Now, again, this is directly operating on raw bytes. So how do we mutate built-in types? So they're collections, they're strings, integers, booleans. So booleans, it's a very simple one. The only thing you can do is make it true or false, flip it the other way, and that's about it. But what if you have a dictionary or a list or a nested set of lists? You have to deal with that in a way that makes sense. And a lot of this isn't something that I've done a lot before. And so there's a lot to be explored here. And this is this sample code is what I did with PiTestAuto Explorer to mutate dictionaries. So it'll either pick a random value in the dictionary, it recursively finds a leaf value, actually not a leaf value, any value in there. If it's a nested dictionary, it may recurse into it and find a value and then mutate that value. But then again, if we're dealing with different types of data, that value could be an integer, it could be a list, it could be a string. You have to have mutators for all of these different types so that you know how to mutate them when you run across them. And yeah, some of the other ones, cutting keys out, inserting keys. Yeah, and this is just to mutate it. I talked about, okay, so crossing over. I think I skipped over, I didn't. All right, so I have a slide that talks about, just a second, let me find it. Oh, okay, it's in the different section. So we will circle back to what crossover means in this setting, but basically it is merging two sets of inputs. So say we have these two inputs, A and B, these two values, integer values in hex. If you wanted to mix them, these are ways you could do it. Now, if this actually makes sense and gets you results, I have no idea. But this is a type of topic that is, or a concept that is used when you're fuzzing binary data. You have two sets of inputs that were previously deemed important, and you might mix them, you cross them over to create a new input that's blended from both of them. So trying to map fuzzing these native data types in different programming languages to that concept may not always make sense. But in this case, maybe it gets you something, but maybe not. All right, so the other part of this is that you also have non-built-in types. You have data structures, you have classes, you have whatever the developer dreamed up. So these will be passed around into the functions that are being targeted in the unit test. One example of code or a project that already modifies these at runtime is GoFuzz, and that is different than Go-Fuzz. Go-Fuzz is the libfuzzer implementation for Go, or basically, it's a fuzzing library that uses libfuzzer made specifically for Go. Phrase it that way. GoFuzz specifically modifies fields randomly on Go objects. And if we wanted to do something similar in other languages, we would have to use runtime introspection. And I will get to the place where that introspection would occur. All right, so let's talk about a corpus of inputs. So a corpus of inputs, I mentioned it seeds your fuzzer. It helps you know a known good starting place, something that gets you relatively deep into the code without having to start from nothing. And it helps a lot with genetic algorithms and hill climbing algorithms. So for example, libpng, just during its normal development, they have collected a series of test PNGs that you could very easily use as a corpus if you wanted to fuzz libpng. And these are intentionally made to To cause libpng to go down different code paths. They're for testing. So there is a lot of correlation between fuzzing corpuses and data that you might collect just throughout your normal process of writing unit tests. Now, some of this data we will be able to derive from the function calls themselves inside the unit test. All right, so but how do we track a corpus of inputs from the unit test? So if we look back at this, we're not dealing with raw data, we're dealing with native data types, maybe collections. So if we want to track that in a corpus, we'll have to think about it completely differently. So we'll want to save function call invocations. We'll need to track the variables that are used during the unit test. Not all variables that are in the unit test will be relevant or maybe even passed directly to the target function. So we'll have to do some analysis of the code to make that work. One of the other things that I'm on the fence about if we need it or not, but I think we would need it. This is something that comes up with DAST a lot and API fuzzing, is we may need to also keep track of sequences of function call invocations. So instead of having a corpus of unique function calls, we may need to even track sequences of function calls. So if we look back at this one, suppose the unit test calls some, and then with the return value, it calls some again with that value as another argument, or it chains a few function calls together. We may need to track that as a series in order to kind of have a corpus that makes sense in the unit test. All right, so this is something that I took from PiTestAuto Explorer. This is the type of data that I was saving for every new crash or error that it detected. It has the, there's the file, here's the source, and these are all of the inputs that were passed to the function. And this is the type of data that is being mutated by PiTestAuto Explorer. And along with these, this is saved in memory. None of this was ever written to disk. So if we wanted to make unit test derived fuzzing that operates on function calls work, we'll have to be able to serialize this to disk so that we can persist the corpus and you reuse it in later fuzzing sessions. And again, it just gets more complicated because we're dealing with non-straightforward data types. All right, so any questions before I talk more about feedback-driven fuzzing and how that would play out with unit test derived test cases? No? Okay. All right, so feedback-driven fuzzing. I've got a few links here if anybody needs them for reference. So genetic algorithms, they mutate data to try to, I didn't add this in here. There's a concept of a fitness function, something that says one input or one thing is better than another thing, more ideal or performant, whatever the fitness function is. And so an item may be mutated and then run through the fitness function to see if it's better, or two items may be merged together and then tested to see if they produce a better outcome. So this is exactly what most of the fuzzers are using now. There's also, if a fuzzer is not explicitly using that, it may be a variant of a hill climbing algorithm where one solution is found and then incremental changes are made to the input. Again, with some sort of fitness function to tell if you're making incremental progress. Oh. All right, so if we look at these concepts with unit testing in mind, we need a fitness function. Code coverage is something that is already used by most testing frameworks, and most projects have that set up, or I will say a lot of them. It's very common. So getting that type of feedback for fuzzing should be relatively straightforward. Unit tests and testing frameworks are set up to already deal with that. Now, this is an example of how feedback-driven fuzzing would work, and we'll walk through it. So let's say we have this function handle data, takes 2 inputs, an array of bytes, chars, and we've got the length of it. If the length is less than 2, it returns. Otherwise, it does some processing. Now, if we call this function and with an empty array of bytes with length 0 and nothing in our corpus, these are the lines that are hit. But we've never seen them before, so it's new coverage, and we add this data into our corpus. All right, so now we choose a new set of data, and choosing the new data would be done by the mutator, optionally using the corpus as a starting place. So now if we run this function again with these inputs, A and 1, we run through the same lines and we don't cover any new code, no new code coverage, and we add nothing to the corpus. Again, if we do it with B, nothing, doesn't help us. Now, let's say we use a previous input B or we decided to randomly put together 2 bytes and we have BA. Now we got past this first check and we're here, which does mean that we had new coverage. And so now we have 2 items in our corpus, and we choose the last item we had and we mutate it and we come up with HA. So now we keep proceeding a little further in the process or into the code. And here we have BA, HA, and now suppose we had mutated HA to have an H lowercase a. Now we've made it even further. Now we're processing HA. And again, the same process would occur since we have these items in our corpus and these tend to be prioritized. That's logic kind of found in the fuzzing framework itself. So recent items in the corpus sometimes are prioritized over old items in the corpus. So the odds of this being randomly created are pretty high. And then the process continues. We take another item from the corpus, randomly mutate it, and try and get further into the code. So if we were to watch it a little faster, it's pretty cool how it works, how if you have that fitness function, that feedback mechanism, you can continuously derive values that make its way further into the code. Now, code coverage is usually the type of feedback that is talked about. It's kind of the easy one, it's the obvious one, but it really can be any type of fitness function. And I wanted to bring this up because it doesn't have to do anything with the code directly. So I wrote something for fun, and it doesn't use code coverage for feedback. It actually uses performance events, and it uses instruction counts and branch counts as its feedback mechanism. So you don't have to instrument the code. All you have to do is run the target binary with these performance measurements in place. Actually, let's look at target.c. So this is what the target looks like. Very similar to the test example, except it's very deeply nested. And it should be very obvious if the fuzzer is more performant than just randomly generating 9 bytes with the correct value. All right, so if we run this, it does occur pretty quickly, and this is using performance events instead of direct code coverage. So my emphasis that I often bring up, that code coverage is just one feedback mechanism, and this is one example of that. So if code coverage is unavailable during unit testing, there are other ways that we can figure out if we are progressing further into the code. And some of those may even be application specific. But again, this BrownBag is about trying to figure out ways to make fuzzing more accessible to developers without them having to be fuzzing experts. All right. So one input parameter is fuzzed at a time. I've talked about this a lot of times. I don't think we need to talk about it again. So now this is where the actual implementation would come into play. And I'm saying it that way because I have not made it as far on the code for this as I wanted to. So that's why the BrownBag is kind of ending around here. But this is my approach, and I am in the middle of this. I'm in here somewhere. But the methodology that I am using right now is to parse the existing unit test into an AST, an abstract syntax tree, and then rewrite all of the function calls. Previously, I had rewritten the Python bytecode to do this hooking, this instrumentation to capture known good values from the original unit test. But that's really not that sustainable, and it's very Python specific. So rewriting the source code should work between major versions roughly of the language, unless it's a very new language, and it would work across languages. You would still have to implement it, but it is a bit more generic and I think a bit more sustainable. And also, you would also need to monitor for code coverage or whatever feedback mechanism you would use. Once you add the code or rewrite the code to capture function calls and monitor code coverage, then you would have to run the test normally to capture those known good values at runtime. So any runtime introspection would happen here at this stage. Once you have captured all of that data, then you'll have a corpus of function calls, and then you can create standalone fuzzing harnesses for all the functions that you want to fuzz. Exactly how that would occur is a bit more to be determined. You could have 1,000 unit tests and you wouldn't create 1,000 separate targets. That wouldn't really make sense to me. I think you would probably round robin through each of them on each fuzzing iteration. But yeah, that is about it. Preserving the imports, the environment, the module hierarchy, everything that you need for the unit test is something that you would have to do when you parse the AST and create the standalone fuzzing harnesses. And yep, that's what the rest of this would be. Draw the rest of the owl. There is a pretty clear path to it. I did not want to put off the BrownBag yet again, just so that I could have code in place or in the state that I want, just so we could talk about it. But yeah, that is the process. And so far, everything does seem to be panning out. Does anyone have any questions? Anything you'd like me to go over a bit more?
Hey, James, thanks for the talk. I do have a question, just a pretty generic one, but so you mentioned that you're currently working on this. Is this, I'd be curious to check it out. I noticed that the one performance fitness test that you had was written in Rust. Is that the...
this one?
Yeah, that one.
Yeah,
right?
So let's see. Rust isn't very high on the priority list as far as work is concerned. It's just more of a new language that I wanted to learn. And so this was something that I did for fun. I brought it up because it uses a different feedback mechanism than code coverage. Yeah, but the same concepts would apply with Rust as well. Yeah, is that where you were going with that question?
Well, yeah. I was just wondering if that was like the thing that you're working on right now. So this slide
that one was just for fun.
Okay.
So I was, let's see. So I'm not sure if I've pushed up the branch. Auto Explorer actually just moves this. All right. So this is, here we go. Resume. Chat. So this is the PiTestAuto Explorer project. Where's chat? Chat, there we go. All right, so this is where I'm starting because I've got a lot of code in place for this. I ran into some snags trying to make it more than MVC, make it work very nicely with PiTest instead of just raw rewriting the source code and then implementing it. So currently, PiTestAuto Explorer, the main branch of it, does do the instrumentation and captures the function calls. It doesn't create standalone files to do the fuzzing. And that's the aspect that I'm currently working on. Once I figured out those topics with PiTestAuto Explorer, then I was going to basically re-implement them in Ruby and Go. Yeah, and they each have kind of different tool sets that could help you with it, but PiTestAuto Explorer would be the one to look at right now. It's the one I've been focusing on.
Cool. Nice. So would this be kind of in the same vein as like the generic SAS idea where it's language agnostic, the fuzzer, or would we be implementing specific?
It would have to be specific to a language. You know, I was thinking about that. It's the source code. All right, so you have the unit test from the project. It's in language X, right? You would have to do the instrumentation on the code. To me, I think the easiest, most sustainable way would be to rewrite the source code, parse it into an AST. So that would have to be language specific. But maybe there's a way to wrap it into a common library where you can abstract away a lot of the language specific things. So if you wanted to add a new language, then maybe all you have to do is implement the specific pieces, right? So like implement the source code rewriting and a way to understand the testing framework so you can create a standalone fuzzing harness. You could wrap this in a single tool, but it would still, languages would have to be added incrementally. You wouldn't be able to knock them all out with one stone.
Gotcha, thanks.
Yeah. All right. Well, any other questions? Anybody else want to see other slides or in general questions? No? All right. Well, cool. Then I will stop the recording here. And I did add a part 1 on this. I will have a part 2 once the code is in place and in a state to show. In the past, when I've merged a lot of technical topics with wanting to talk about the code, it tended to get really messy presenting anyways. So I'm kind of liking having it split up. So next time we'll be talking specifically about the code.